Hello everyone and welcome to Sky Scholar. Today we continue with our analysis of the microwave background by reviewing the Planck foreground analysis. In these two videos I emphasize the presence of the galactic foreground in the frequency map, both for the Planck and the WMAP satellites. I also stated, based on extensive experience in the laboratory, that it is absolutely impossible to extract a weak underlying signal from a strong overlying signal without either perfect a priori knowledge or ability to manipulate the signal at the source. It is physically unreasonable to remove the foreground despite the pronouncements of the cosmologists. You can learn more about this argument in this paper. In the last video, I described the point source problem and how these must be treated with foreground component analysis. The point sources must then be masked when making the final CMB maps. That in itself argues that the CMB maps have nothing to do with cosmology, as there are now over 100,000 point sources. For the time being, we ignore the monopoles and the dipoles, as the Planck team gets the actual priors for the monopole from the Kolbe-Firis data and for the dipole from WMAP. Before Planck, the WMAP team had also tried to address the galactic foreground, and in doing so, NASA presented this figure from which one can get a general idea. At low frequency, the astronomers believe that the foreground is primarily composed of synchrotron radiation, spinning dust, and free radiation. At high frequency, they are mostly concerned with thermal dust. What does this all mean? In simple terms, synchrotron radiation occurs when a charged particle is accelerated radially, often through the effects of a magnetic field. Spinning dust emission is an invention of the cosmologist. Initially, it was known as anomalous emission because its origin was unclear. Then the astronomers came up with the idea that a dust particle might have an electric dipole moment. If it does, then it will emit microwave radiation as it rotates, hence the new name spinning dust. Free microwave emission occurs when a free electron collides with a positive ion. The emission from thermal dust was initially thought to be much like blackbody radiation. However, today it is treated as a gray body, emitting with a temperature near 20 Kelvin. They are like black bodies, except with reduced emission at every frequency. Today, the astronomers have added a couple of more components to the galactic foreground, but remember that all of this is just playing with models. The temperature foreground maps associated with the 2015 data release are described in this paper. Here are the temperature foreground maps, each associated with a different component. There are a total of 6 components, and as you will soon see, some are further subdivided. The first 3 components correspond to the anomalous emission we saw above, also known as emission from spinning dust. Then comes synchrotron radiation and free emission. These mechanisms are believed to be important at low frequency, but the cosmologists can never be sure of what's going on. They can only model. Note that these first 3 maps are plotted at lower resolution. At the higher frequencies, the astronomers now add the emissions from transitions within carbon monoxide. In addition, they consider line emission at 94/100 GHz from molecules like hydrogen cyanide, cyanogen, the formal cation, and carbon monosulfide. This is all guesswork, of course. They are simply looking to create a narrow emission at 100 GHz, and soon you will understand why. Finally, for frequencies above 100 GHz, they present thermal dust modeled as a gray body. There is also polarization maps associated with thermal dust and synchrotron radiation. Polarization occurs when the electromagnetic radiation detected has different horizontal and vertical components. In unpolarized light, these components have equal magnitude. In order to generate these temperature foreground maps, the Planck team combines Planck data with 9-year WMAP results. It is important to note this step, as it serves to help ensure that the Planck CMB data produced will agree with the WMAP results. The more than 100,000 point sources we discussed in the previous video adds another means of making the results agree. As such, any perceived agreement between WMAP and Planck is a myth, as the results were never analyzed independently. In the 2018 data release, described in this paper, the 2015 foreground analysis still governs the creation of the temperature maps. However, the WMAP results are not used when producing the 2018 polarization maps. The reason once again is clear. If the foregrounds are removed blindly without the influence of WMAP, the results between the satellites will not agree. The WMAP satellite also detected polarizations, but the results were not painted as definitive. As a result, unlike the temperature data, they can be easily overturned. So remember, when removing the foreground, the PLANCK team marries its data with the 9-year data from WMAP, and that helps ensure that the final CMB temperature maps will reasonably agree. In addition to using the WMAP data for foreground maps, the PLANCK team also relies on the 408 MHz all-sky map produced in 1982 by Haslam et al., as you can read in this atlas. The PLANCK team claims that they must introduce the 418 MHz map, as synchrotron radiation is determined almost exclusively by this survey. Sounds like good logic, doesn't it? But in my opinion, there is something else much more important at stake. The 408 MHz atlas has much lower resolution than the Planck low frequency instrument. So why introduce a map which is more than 30 years old to alter the results with the expensive Planck LFI? The answer comes in noting that in order to make use of the 408 MHz data, the PLANCK team must first degrade the resolution for the LFI used to make the low frequency, spinning dust, synchrotron, and free foreground maps. This is very convenient, and it serves to mask the tremendous year-to-year instability that we noted in the LFI at 30, 40, and 70 GHz in this video. The PLANCK team, by lowering the resolution on these maps, makes the yearly changes go away, as they smooth out adjacent regions of the maps. How convenient! Now the proof that the Planck LFI data had nothing to do with cosmology, which was noted in this video, has been erased using resolution changes. Yet the PLANCK team is completely unjustified in changing the resolution of the LFI channels without first characterizing their stability for cosmology. I noted that the sky signals received at these frequencies were not stable, and now everyone understands how the PLANCK team overcame that problem. Furthermore, for each pixel in the map, the PLANCK team uses a total of 12 degrees of freedom. Talk about unreasonable. Even more stunning than that, for the foreground analysis, they are throwing away a huge fraction of the Planck data. They write, some Planck detector maps are affected more strongly by systematic errors than others, and in the following temperature analysis, we exclude the worst channels in order not to compromise the overall solution. In fact, Planck has a total of 31 potential detector and detector set maps. In the foreground analysis, they end up rejecting an astounding 10 from further treatment, as you can learn in this paper. At 857 GHz, that represents 3/4 of the data. For 545, that's half the data. Where else in science is it permitted to discard so much of the acquired data without serious questions being raised? Next, they do not like the residuals produced in the maps when they incorporate the remaining 545 and 857 GHz data. How do they address that problem? Simple. They add white noise to their data. By doing so, they have now essentially thrown away all real data at 545 and 847 GHz. I can think of no other example in image processing where white noise is deliberately added to degrade an image. In imaging, noise is the enemy. It is something to eliminate, not add. Now let us look more closely at the low frequency maps. Here is the Planck map for anomalous emission. One immediately notices the lower resolution. This map is important as it represents everything that did not quite fit in the low frequency data. The Planck team gives it a nice name, getting rid of the anomalous emission and invoking spinning dust, as if a new name creates real understanding. They adopt a two-component model for the problem, yet state, we emphasize that this is purely a phenomenological model and we attach no physical reality to it. In the end, they really have no idea what causes anomalous emissions. Next, we move to synchrotron radiation, both for the temperature and the polarization, as synchrotron radiation is said to be highly polarized. Once again, the resolution is greatly reduced, hiding any year-to-year instability problems. The same holds for the Q and U polarized maps. The resolution is gone. Next, we come to free emission. Again, the resolution has been degraded. How can anyone believe that the Planck team can separate these three components into 5 distinct maps? This is nothing but an illusion. The Planck team speaks of spinning dust, synchrotron, and free emission, but they can never really know what's happening in the galaxy, as all these signals are degenerate. Next, what happens at high frequency? Once again, we know from the last video that the Planck data is plagued with year-to-year instabilities. But in order to solve the problem at high frequencies, they take a different approach. Rather than degrade the resolution once again, this time they invoke line emission in carbon monoxide and at 94/100 GHz. They write, therefore, while components with continuous spectra very nearly vanish in detector difference maps within single frequencies, line emission does not. That is why the Planck team resorts to line emission. It serves to hide the instability in the high frequency channels without degrading their resolution. But what they actually have is simply noise which they can never understand. In any case, relative to line emission, we first come to the transition between low and high frequency channels, the 94/100 GHz emission map. Once again, this is plotted in reduced resolution and serves to mask the instability problems at 100 GHz. It is evident that a new mechanism for line emission was introduced just to deal with instabilities in that channel. Note also that the power in this map is spread rather evenly throughout the map. There are plenty of strong signal regions outside the galactic plane. Next, have a look at this carbon monoxide map. Can you see how much power there is outside the galactic plane? There are plenty of pixels in dark red or blue at elevated latitudes. In fact, with this map, the Planck team is now giving tremendous line emission power throughout their maps. That serves to hide the enormous year-to-year instability problems they face at high frequency throughout the sky. Since line emission has nothing to do with cosmology, the Planck team gets to take it out in making their final CMB map. In doing so, they claim that their data was linked to cosmology. But in reality, they are simply ignoring what the sky was telling them. I have nothing to do with cosmology. They created stability through processing. This is an extremely important point and bears repeating. They created stability through data processing. Most will never notice what has been done to the yearly maps and how the instability problems were eliminated. Since cosmologists believe that the remnant of the Big Bang is speaking to them, they impose upon the sky a stability which was simply not there. The carbon monoxide maps have also been separated for the 0-1 transition and the 2-1 transition, as you can see here. That gives more degrees of freedom for removing the foreground and for hiding map instability problems. Next, we come to the high-resolution temperature dust map and the polarized components for thermal dust, which the Planck team argues dominates at high frequency. Again, this provides yet another means of hiding stability problems because thermal dust is allowed to be unstable. It is clearly not a cosmological signal. But in their paper, the Planck team boasts of their results, writing, HFI observations are strongly signal dominated at all angular scales above 7 minutes full width half maximum. They cannot make that statement as they have no idea if cosmological signals are even present. They impose its presence at lower angular scales precisely because that was the only way to hide the fact that no stability existed at the higher resolution. Twice in the foreground paper, they speak of intuition helping to guide their data processing. They first state, it is useful to review the various model components that are relevant for this work, with the goal of building intuition concerning important degeneracies and residuals that may be observed in various goodness of fit statistics. Later they state, before presenting the actual baseline results, it is useful to visually consider a few specific data combinations in order to gain some intuition regarding the power of these data for constraining specific parameters. But intuition has nothing to do with science, and never before have I seen the word used in a scientific paper. They know that their models simply represent some of the many possible approaches and write, we emphasize, however, that these models are not unique, but instead represent physically well-motivated models that are able to reproduce the current data. What does well-motivated mean exactly? There is nothing well-motivated relative to the scientific objectivity in the Planck data analysis. Despite their claims, the Planck team argues that more experiments could help break the degeneracy which exists for the synchrotron, free, and spinning dust components. In reality, nothing can break that degeneracy. So there you have it. In order to complete the foreground analysis, the Planck team discarded 30% of their data. They allowed 12 free parameters for each pixel. They married the Planck analysis to WMAP to help ensure reproducibility. They deliberately reduced the resolution of the low-frequency instrument, thereby hiding their instability. And they added components like spinning dust with little or no scientific basis. At high frequency, they added white noise to the remaining 545, 847 channels, and they added line emissions for carbon monoxide and at 94/100 gigahertz in order to account for yearly instabilities in those channels. They did all of this in addition to creating more than 100,000 new point sources. It should now be clear that the Planck anisotropy maps have little more to offer than wishful thinking relative to cosmology. No authentic separation of foreground components will ever be possible, and such approaches will never have any true merit in science. Well, that is all for today. If you enjoyed the video today, promote the channel, mention the video to your friends and your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on our next video.